Hey everybody. In this video, we're going to continue our study of the first derivative test and what it reveals to us as far as the function is concerned. So if you see f dt, that just stands for first derivative test. Well, I can find the first derivative for several reasons because maybe I want to know where the regular graph is increasing or decreasing. Oh my. So we're going to use the first derivative test for increasing and decreasing intervals. And to locate extrema, to locate relative extrema. Relative, if you remember, it's just interior. Relative extrema. Interior, if we have a closed interval. All right, so we're going to use the first derivative test for increasing, decreasing intervals and relative extrema. This is not starting out good. All right. If we don't have a calculator, we want to know where this graph is rising, increasing, falling, decreasing, where it has mins, maxes, then we need to know something about its derivative. Notice that the function itself exists everywhere. As a matter of fact, the derivative is also going to exist everywhere. And I believe that was a square. I'm hoping that kind of straightens itself up. All right, the derivative exists everywhere, so let's find critical numbers. Set the derivative equal to 0. Let's make our numbers easier to work with. So I'm going to take out my common factor. I don't know why it's wanting to disappear. It's early. All right, so our critical numbers are x equals 1 and x equals -2. So remember what that might look like when it's presented to us. We might be told that these are the critical numbers, okay, in this kind of format. This notation is just more descriptive of what's going on the graph. So I'm hoping everything's all good here. I factored, set each factor equal to 0. Yeah, it looks good. Okay, so what I'm going to do is I'm going to come over here now that I've established my critical numbers, and I'm going to build my f prime number line. Okay, so this is an f prime x number line. And notice that my function itself, I'm going to take a peek in at my function. My function exists everywhere, so I'm going to represent all real numbers, the domain with the entire number line. Right here I have two critical numbers, so in order, at -2 and at 1, I have two zero slopes. So what happens is two critical numbers will divide this f prime number line into 3 sections. So what we're going to have to do is 3 test intervals. So I'm going to test into f prime a number less than -2. I'll just go with -3. I'm going to the derivative. Instead of plugging in -3 here for every x, I'm going to plug it into the factored form because all I care about is if the answer is positive or negative. All right, replacing x with -3, the result is a negative. Replacing -3 in here is a negative. So a negative times a negative is positive, and a positive times a +6 would be positive. So the graph of the regular function, this cubic, is rising, positive slopes, until it gets to an x-coordinate of -2. All right, in this interval right here, let me go ahead and record that as greater than 0. In this interval, 0 would be an easy test value. So plugging 0 in, I would probably use the original f prime here, the unfactored version, and get a negative number. So that tells us that at every x value between -2 and 1, the slopes will always be negative. So it appears that the function is going to have a maximum, a relative maximum, because the slopes change from positive to negative. That is, the function goes from increasing to decreasing. It's going up, and then comes back down. I'm going to test just 2 over here. In the factored version, I have a positive factor. Positive times a positive. That results in a positive product. So this tells us that the function is, if it helps you, this tells us that the function is increasing, decreasing, and increasing. If that's a visual help for you guys, then write it in. All right, we're going to take our organized work and we're going to report what we found and we're going to justify our answers. So let's start with the increasing, decreasing. So the name of the function is f. So f is increasing on, we're going to do open intervals. -infinity to -2, 1 to infinity. Let's justify. I'm going to shorten and abbreviate because the slope f prime, the f prime values are greater than 0. And because I have the intervals with parentheses here, I don't have to worry about the or equal. F is decreasing where the slope of the graph is negative, and that happens to be from -2 to 1. Because f prime is less than 0, and that was a 1, I believe. All right, and one more thing we want to consider is, do we have any relative extrema? Well, as you work your way from left to right, we can clearly see that we're going to have a maximum at x equals -2 and a minimum at x equals 1. So f has a relative max at x equals -2 because f prime, the slopes, change from positive to negative. Okay, hopefully you have more room than I do there. This graph also has, the graph of f also has a minimum. F has a relative min at x equals 1 because f prime changes from negative to positive. The slopes go from negative, falling, to rising, okay, function, negative to positive slope, so it has to have a minimum. It bottoms out. And we could sketch a graph if we wanted to, but I think it might be good if you just picked up a calculator and checked to make sure that you see that your graph is going up, up, up. Okay, what you could do is go up, it flattens out, but it comes back down because of these negative slopes here. It comes back down, it has a minimum, and then it continues by going up. Now, where exactly is that occurring? At what points? I don't know, but I could plug these two critical numbers back into the regular function to nail down those ordered pairs where I have a max and where I have a min. All right, let's look at another interesting example. Notice, if you will, that this is not a polynomial function. It's a cube root. Okay, this is the cube root of quantity x minus 1. It might be helpful to graph it first to get an idea of what's happening to confirm our analytical work. Others of you might want to do the analytical work and then look at the graph and go, yeah, that makes sense with what I'm finding. All right, let's find out where this graph is increasing, decreasing, and if it has any mins or maxes, relatively speaking. We don't have a closed interval, so we're not talking about absolute extrema. We're talking about relative. All right, looks like we need to find the derivative first. Before I do, I always kind of pay attention to the equation. Notice that the function exists everywhere. There is not anything that I could not allow x to be, even though I'm dealing with the cube root. Remember, odd roots, it's okay to have a negative radicand. Radicand is just a word that means what's under the radical. So it's okay to have a negative value here, so there's no limits for my x value. X can be anything. So the domain being all real numbers, the graph is going to continue across your entire calculator screen no matter the window setting you chose. So we've established that. Every x works. So let's go ahead and find the derivative. Chain rule. The derivative of the inside function, the derivative of x minus 1 is just 1. So in fact, we're done here. Okay. If you wanted to show that, that wouldn't hurt. Okay, let me clean this up a little bit. With those negative exponents, I'm going to want to make them positive. So I'm going to create a fraction. 1 stays on top, 3's down here. This becomes, let's see, the cube root of quantity x minus 1 squared. I don't know why everything's wanting to disappear so soon. Okay, taking a look at this derivative now. Notice that the derivative can't ever be equal to 0. Okay, if I set this derivative equal to 0 over 1 and I did cross products, I'm going to get the statement 0 equals 1, which is false. So, and the only way for this fraction to ever be equal to 0 is if what's in the numerator would equal 0. Well, I don't have a variable up here. Kind of think about what I just said there, and if you need to pause and rewind, not a bad idea. This derivative will never equal 0 because there's no way this numerator will ever be anything but 1. So we're still investigating critical numbers. Well, where is this derivative 0 in the denominator? Remember, we don't want to divide by 0. So if I set the denominator equal to 0 and I solved it, okay, I'm going to get that x equals 1. X equals 1 is going to make us have a 0 in the denominator. So you could show the work by setting the denominator equal to 0 or setting the derivative equal to 1 over 0, cross products, okay, which results in the denominator equals 0. Okay, you're going to end up with x equals 1. So when x equals 1, we have a critical number. F prime of 1 equals not 0, but does not exist. This is still a critical number. So I want you to think about that for just a second. If x equals 1 is a critical number, okay, and x equals 1 did exist in the regular function here, okay, something interesting is happening here. It may be a sharp turn. The other situation is it could be a vertical tangent. Okay, let's see what's going on with our f prime number line. Anyway, let's build the f prime number line. Remember, the domain for the function is all real numbers. I would adjust this number line accordingly if it wasn't all real numbers. Make sure you have f prime here. Take a look at your notes. Make sure you have f prime here. The only critical, again, the domain is all real numbers. There's no breaks on my number line. Okay, the critical number is 1. And notice how I'm going to note that. I'm not going to put a 0 slope. I'm going to put a does not exist slope. All right, test interval, f prime of 0. Goodness, when I plug in 0 here for x and subtract 1 and square it, it's positive. The rest of my answer is going to produce a positive number, so all the slopes are positive. So what does that mean? It means that the graph of the function is increasing to a does not exist situation. Well, the function's still there because the domain's all real numbers. So it's rising, rising, rising. It's either going to be a sharp turn or a vertical tangent. If it turns around, the slopes are going to have to be negative. All right, f prime of 2. Plug in 2. Subtract 1, you're going to get a positive output. So if we think about what that's telling us, the function's increasing, does not exist, the slope doesn't exist, and then it continues increasing. Well, the only thing I can think of is perhaps a graph coming over here that's increasing, 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 does not exist, must be a vertical tangent, because if it was a sharp turn, it'd fall back down. So it must achieve a vertical tangent and then perhaps continue to increase. I might suggest go to Y1, type that in, visualize what that graph's doing to make sure that it matches up with this information. Okay, so let's go back here and answer some questions. Okay. F is increasing on all real numbers because F prime is positive, or F prime does not exist. Just one time the derivative does not exist, but we have to include that. Okay. I think you would get full credit if you just reported this as an answer right here and didn't specify this situation. But I think it's still good to do so. All right, F is decreasing, oh, nowhere. So we don't have to even mention that. Oh, also, are there any mins or maxes? Well, do I have a sign change on my slopes? Does the slope of the graph change from positive to negative or negative to positive to indicate the graph's turning around, which contributes to your extrema, your relative extrema? No. So we have no relative extrema. So we're finished here. In the next video, I want to do one more problem with you. See you in a second.